Yeah, I want to thank everybody for attending. Our presenter today is Dr. Samir Shende. He's a research professor at the University of Oregon and known very highly and known for his work in the Tau visualization system, the organization. He's president and director of ParaTools and ParaTools SAS France, and he's the technical lead for all things ParaTools and Tau. His research interests include scientific software stacks, performance instrumentation, compiler optimizations, measurement and analysis tools for HPC. So we're really lucky to have him here to present in person about this very well-known visualization program called Tau. And with that, I'll turn it over to you. Samir, you are free to start sharing.
Thank you for inviting me, Meg. And today, my talk will focus on the Tau performance system and E4S. This is the URL, just tinyurl.com/E4S tut. I have set up an AWS cluster. It's ambitious. I hope we get to do hands-on with a demo at least and show you how to use Tau with an HPC application. We have compute nodes. We have login nodes where each of you can have your own separate home directories and launch Tau. And it's all there in this E4S tut. And those who are anxious to try the hands-on session, you may want to go straight down to the Tau hands-on part, which starts on slide number 84, if you want to see how to connect to this system that we have set up and log in and launch a remote desktop like this and get a terminal window and run the tools. Okay. So with this, let me just go straight into the Tau performance system. It's a very versatile profiling and tracing toolkit that supports a number of different runtimes, including MPI, CUDA, ROCm, DPC++ with level 0, SYCL, and OpenCL, OpenMP with target offload directives to the GPU, and OpenACC. We support a number of different languages, usual languages like Fortran, C, C++, Python, and also we have support for source instrumentation using PDT and SaltFM. We support access to hardware performance counters. And if your application is using some timer library where you have your own start and stop calls, whether they come from perf stubs or 5prof or cam timers or Cocos, you will see that Tau can understand those timer calls and automatically generate the start-stop calls for the Tau instrumentation. And you'll be able to view the performance data at the same level of abstraction that the developer intended. We support a single tool called Tau exec, which can be used to launch uninstrumented, unmodified binaries. So you can see the performance data in ParaProf, Perf Explorer, pprof for profile data, and for trace visualization, we have tools like JumpShot, which ships with Tau, or third-party tools like Vampire and Perfecto.dev. You can find out more about Tau at this URL. And it's important to note that you do not need to modify your source code. You do not need to modify your build system. You do not need to modify even your binary. You can simply launch that binary using Tau exec and then enable other options of Tau. Well, this is how it looks. If you have an MPI application and you're running it, say, with MPI run np16 a.out, you just add Tau exec-ebs after loading the Tau module. If you have configured Tau with multiple options, such as pthread, CUDA, ROCm, you can enable those tags using the -t parameter. And then immediately after running your application, you do not need to change or modify the profile files. You can just launch pprof or paraprof or GUI tool and view the data. If you are using Vampire as a trace visualizer, you can enable the creation of OTF2 files and launch Vampire right after the execution, or if you're using Chrome or Jumpshot or Perfetto.dev, then a merge and a conversion of the trace file is required, and then you can launch it like this. So to recap, if you have an uninstrumented program that's say a.out that's launched like this, you just launch it with tau exec with different GPU options. If you're using AMD GPUs, you'll use -ROCm, kubectl for CUDA profiling tools interface for NVIDIA GPUs with unified memory. Level 0 is for Intel GPUs. OpenCL, OpenACC work across GPUs. You can track I/O. You can track OpenMP with the OpenMP tools interface with OMPT. You can set additional environment variables of tau, such as this support level for OpenMP or memory debug options with leak detection. And you can enable event-based sampling where you periodically interrupt the program using the -EBS. And you can set hardware performance counter metrics over here as well. Advanced features of tau include adding hooks to support instrumentation of your code at the source level, at the library level, at the executable level. All these events flow into generation of profiles or traces in the measurement module. And then you can analyze the data using ParaProf or third-party visualizers such as Vampire or Jumpshot or Perfetto.dev. In case you're wondering, what is it that tau can show me? Well, it can show you how much time is being spent in different code regions. These could be routines, they could be outer loops. Even within the loop, you can see the time spent in each statement or the time spent in OpenMP loops, in kernels running on GPUs, and even data transfers between the host and device. And instead of time, you could measure hardware performance counter data, such as floating point instructions, data cache misses. You can measure the time spent in an MPI barrier within a collective operation. This will reveal the bottlenecks in your program. As you scale up your codes, you may be running them on thousands of nodes, and you will see that a significant amount of time is being spent in collective operations. Well, within those collective operations, a lot of time is just wasted in a collective sync barrier. And this is the time that tau can show you on a per process basis without generation of expensive, costly trace files. It can do this just with profiling with the tau exec command. You'll see an MPI collective sync, the time wasted in a barrier when you could be doing something more useful. This is typically due to an imbalance in your code. It can measure the memory usage of your code, where the memory is allocated, deallocated, and the memory footprint. By footprint, I mean the total amount of memory taken in your process. This includes the stack, the heap, the data, the text, the uninitialized data or BSS, all of these 5 components, and the high water mark during the execution. So you could see that this process reached, say, 2 GB of RAM usage. And then you can assess the memory usage of your application. You can see the energy usage, the I/O characteristics, even how it scales. And to do this, you need to add hooks. These can be direct or indirect. With direct instrumentation, you have function calls that are instrumented with a start and a stop timer with a probe. And we've all done this with, say, the get time of day call, right? Around loops, around functions. We also have the ability to trigger an event with some data. It could be the message size sent by a process. It could be an atomic event or a context event, which shows you which function was executing in a call stack when that event was triggered. An event such as the amount of memory used by the program or the I/O operation that takes place in the code. Now, to add hooks to your code, we have support for a preprocessor-based source instrumentation using SaltFM or PDT packages, where you replace your compiler scripts with a tau compiler script, such as tau cc.sh. And then you can supply it a selective instrumentation file to filter the events based on include and exclude lists. Now we can also do this with the compiler. We also have a LLVM plugin that allows you to operate at the IR level and make very detailed, very compact instrumentation during the compilation. And again, you use these compiler scripts, but you do not need to use source instrumentation or compiler-based instrumentation. You can take an unmodified binary and simply launch it with tau exec. Now you can configure tau with many options, such as with MPI, with CUDA, and each of these configurations creates a unique stub makefile, which encodes in it the paths to the CUDA library, the path to the compiler or MPI. And then if you were using source instrumentation or compiler-based instrumentation, you can set a tau makefile as an environment variable to point to that configuration. Each configuration of tau creates a unique stub makefile, and the same tags are used by our tau scripts. So you can simply replace an MPI compiler with a corresponding tau compiler, compile your code, run it, and then see the data in pprof or paraprof. So if you see a tau configuration, you'll see there are multiple tags, one with, say, MPI with Intel compilers, with GNU compilers, with OpenMP tools interface with MPI or with pthread. And you can use the tau exec command to just launch the uninstrumented binary with these tags, which correspond to one of these configurations. And if you were instrumenting the code, you will have to set this tau makefile variable and then substitute the compilers like this. But you do not need to source instrument. You can simply launch it with tau exec and enable event-based sampling like this with EBS. Now, we do have a sophisticated source analysis system, but some of the parsers that we included in this were getting old. So we are working to update these parsers through the program Database Toolkit. When you use PDT, essentially you're parsing the source code and adding hooks at the function boundaries with the help of an instrumentation specification file and creating a copy of the instrumented code, which is then compiled and run. It looks like this. With PDT, there were some issues with C++ and Fortran. And so we are now using a system called Salt FM to add hooks to Fortran and to C and C++ using LLVM compilers, using just a plugin. And this is part of a NASA SBIR, where we have implemented support for performance instrumentation. Essentially, you generate the instrumented code and launch it, and it generates profiles or traces. Profiles show you how much time was spent in each routine, while traces show you what's happening at a given point in time along a timeline display. So you can see this message was sent from this process to that process at this time. While profiling shows you the summary statistics, the aggregate data. And then if you have hooks in the function at the entry and exit, you can calculate the inclusive and exclusive time. Now let's consider this function foo. Let's say it takes 100 seconds and it calls a function called bar, and we have added hooks for entry and exit in both foo and bar. Then it will say that the time spent in foo was 100 seconds. And if, say, bar takes 20 seconds, then it will say the exclusive time in foo outside of the instrumented bar is 80 seconds. And with this, you can create a flat profile, a call site profile, a call path profile, a whole loop profile, or a limited profile, and go all the way to trace files, which have all the event logs, which are time-stamped, and you know where that event took place. To generate the performance data, you can have instrumentation probes that are inserted in your code, which have a start and a stop call. Or you can have indirect instrumentation, which is through sampling, where you do not need to modify the code. And with sampling, you get hooks in the code so that every few milliseconds, you get a sample, an interrupt, and you can see where the program was. This is a very simple mechanism. If your application, say, runs for 100 seconds, and if you have an interrupt every second, you get 100 samples. If 30 samples come at this particular line of code, then it will say 30% of the time was spent there. In instrumentation, you have a start and a stop call at the function entry and exit. And then you can get detailed information about the inclusive and exclusive time spent in that. So we have a way to throttle events that takes care of lightweight functions that may be instrumented and get called frequently. And then it generates a profile file, which is viewed in ParaProf. This is our browser. You can see ranks of MPI listed as nodes here. And then you can see the colors which represent the total time. This is not a timeline, but a total time in that function. If you just go to options and don't stack these bars together, you can see the shape of each of those functions called, say, 16,884 times, and this wait took 12.2 seconds. If you click on a node, you will see a top level timer for the inclusive time, which is the .tau application. This is the total time spent in the application thread. And you can see the time spent in individual functions like this. Here is the top level function, main. You can see the exclusive time, which is very interesting, which shows you the time spent in the top routines and code regions. Here I see that there is a point solve 5 in this application called Fun3D, and it's occurring at this file, at this line and column to this line and column, and it's within a point solver function. So you can see the loop and which are the top loops in your code by instrumentation. With call path profiling, I can generate call paths, not just the flat profiles. Here I see what happens when a particular function is called along a calling sequence. So I see that this point solve 5 is taking 43.6 seconds exclusively, and it is called along this calling sequence. If I set the call path depth to 100, likely it will go all the way up to the main. The default is 2. And you can see these call paths with an arrow, which shows you this particular call path along this calling sequence on all the ranks. So these are MPI ranks, and you can see the time spent in each of them along this calling path. With call site profiling, I can partition the time in a particular function. So here, MPI receive is taking 14.6 seconds, but the MPI receive in exchange 1 at the call site of line 68 in exchange 1.f takes 12.6 seconds. In the same file, in the same function, at line 86 instead of 68, it takes 2 seconds. So you can partition the time in MPI receive along a particular call site. So 12.6 seconds at line 68, 2 seconds at line 86, and so on. We can also see call path thread relations window, where you see for a given function or given code region, the immediate parents and immediate children. So you can see what happens in this point solve 5, where it was called 1500 times. It took 53 seconds of inclusive time. 46 were spent exclusively in this region. And 6.3 seconds were spent calling a single matrix complete transfer function. So this 46 plus 6 plus 0.3 adds up to this 53 inclusive seconds. Here, MPI Bcast is called 27,956 times. It took 29,450.457 seconds. And you can see its immediate parents, like this parent for MPI Bcast, which is taking 16.7 seconds in Bcast when it was called from this integer matrix Bcast. So the broadcast of integer matrix is taking 16.7 seconds here. And you can see this scalar broadcast is taking 5.4 seconds here. I had mentioned this timer, a timer that can reveal the bottlenecks in your code, a timer that can show you the time spent wasted in a barrier operation which is inside a collective. And this is the MPI collective sync time. In this particular case, this application spent 574 seconds stuck in a barrier. Now, your first natural question is, which collective operation was responsible for this? And in immediate parents, I can see that MPI all reduce was responsible for 382 seconds out of the 574 seconds. In this call path relations window, I can see that out of the 15,177 calls to the barrier, 9,543 calls came from all reduce. Bcast was responsible for 4,311 calls, and it contributed 89.8 seconds of time wasted in a barrier in this application. Now here you can see that the instrumentation used CAM timers, which were calls that were already inserted in this XGC application. And you can also see that we have support for COCOS. COCOS is a system for performance portable programming. And here the parallel for written in C++ has a first argument of set buffer particles D. This is the argument that the user has written and understands, and Tau can capture that argument instead of large template instantiations and show this time for the parallel for. And you can see immediate parents, immediate children, and even compare ranks. This makes for some very easy to read profile files where you can see that the time wasted in a barrier was 574 seconds on rank 118, while it was just 187 seconds on rank 22. And you can see where this waste comes from. This MPI all reduce called from the fcall mult red2 timer, which comes from this conv.io collision source grid main loop calling sequence. So you can track exactly where your application was wasting time and see a region of code that you can very easily understand. Like this parallel for used Picard as the first argument, and then it was doing this solver step. You can see the time spent in a particular loop across different ranks, and even along a timeline display. This is a timeline, and you can see the arrows showing the communication calls to generate such a trace and see it in jump shot, which comes from Argonne National Labs and is shipped with Tau. You just need to turn on tracing, run your application, and merge and convert the trace files and launch the jump shot tool. But this is not the only tool that we use for trace visualization. We also have support for Chrome browser, and this is the same Chrome browser that you already have on your laptop. You can just enable Chrome://tracing and load the JSON file that is created when you run the application and merge and convert the trace file to the JSON format. But I would recommend that you use perfecto.dev, another tool that comes from Google. Both the Chrome browser and perfecto.dev come from Google, and you can launch this through a website called perfecto.dev. And after you run the program with the Tau trace enabled and you merge and convert the trace files, you can load the trace and see it in the visualizer. Here you can see a flame graph along a timeline, and you can see what each process and each thread within that process was doing, and click on an event to see where it's executing and for how long. There are CUDA streams here. There are flow events that connect the thread with another thread. And you can see very easily along a timeline display what the application and all its MPI ranks were doing. We also have support for OTF2. And if you're using the visualizer from Vampire, you can visualize these trace files. I should mention that Vampire is a tool that was developed at TU Dresden in Germany, and it's a commercial trace visualizer. One added advantage of using OTF2 is that you do not need to merge or convert large traces. After you set these environment variables and run the application with tau, you can immediately launch the trace visualizer without the merge or conversion stage, which can be very useful. And Vampire can be used to visualize the traces. You can see over here that COCO's parallel for calls have the names of the events that were encoded in the parallel for, and you can see those events occurring along a timeline. It's important to note here that there was no change made to the source code or the build system or the executable or even the COCOS library. Tau does the handshake and gets those COCOS events with unmodified binaries simply by launching them by using tau exec. And then you can see with event-based sampling what's happening in the rest of the code. You could see that at line 2705 in this file, in this function, it was taking so much time. And this is by just turning on event-based sampling or EBS. You can see this information in a thread statistics table. Here you can see the number of calls, but I should mention that if you see context or summary or sample, these calls represent the number of samples that it received. And this is an estimate of the time spent based on event-based sampling. So you can expand this summary for this routine and see line by line how many samples you received. For example, 14 samples were received and you at line 228, and if I say show source code, it will show me the source. When I receive a sample and interrupt the program, I can also unwind the entire call stack. And if I unwind the call stack using EBS unwind set to 1, then I can expand each of the call stacks and see where the time spent in MPI receive was coming from. And in this case, there is a barrier all function which is taking this time. And I can go and unwind all the way down to the system calls and internal functions and see the function name, the source file and line number, and where it comes from in the application by unwinding the call stack. We can also look at the context event window, and it will show us the data transfer from host to device, device to host along a sequence, the call path. And this is using a tool called tau Python, which is the same as tau exec in its arguments, but it instruments the Python codes. You can see the CUDA memcopy operations from device to host and host to device. And you can also peek inside system libraries. Now, this is interesting because you can see inside vendor-provided libraries whose source code you obviously do not have. Here I'm seeing Python instrumentation as well as MPI. And this is a Spectrum MPI from IBM. And I can see the internal PAMI calls, the pthread spin lock calls, and see what that MPI was doing by collecting so many samples within the bcast operation. And also you can see samples for other kernels that are launched. And you can see bytes, the write bandwidth, read bandwidth. You can see on a file-by-file basis what the application was doing. We have a 3D profile browser. I hope to show you this in a demo. And it shows you MPI ranks, it shows you functions, and then the location where these crosshairs meet. This is the function and the head where you can see the height and color value, which you can again set. And where these crosshairs meet in the 3D display, you can see the function name. and the height and color values. We also have a communication matrix display, which shows you the information from sender to receiver. And what is interesting is that Tau supports many different runtimes. It includes support for MPI, pthread, OpenMP, OpenACC, OpenCL, even OneAPI, CUDA, ROCm, Cocos, Python, and you can mix and match these. Just last week, I was working with a user who had a code which used the AMD GPUs, but he used Python with MPI and OpenCL. So he needed support for tracking the execution of kernels running on the AMD GPUs. But he also needed the instrumentation at the MPI level, at the Python level, and the rest of the C code. So you can mix and match these different runtimes with Tau and just configure Tau with these options and then launch Tau exec with the intended backend. Tau also supports rewriting binaries. And using Dynast API, you can read a binary and rewrite it. What's interesting is that you can also do this with shared objects. So I could take, say, libhdf5.so and rewrite it, and then use that rewritten binary in a different directory to launch my application. Now, what happens here is that your application is uninstrumented, but you're using an instrumented libhdf5, and then you can generate profile data. You can even supply a selective instrumentation filter file and say, I'm only interested in the high-level API. I'm only interested in instrumenting. Here is the include list, which has H5 hash or the clean star. That means only functions that begin with H5 should be instrumented in the HDF5 library. And then I can see all of these calls with an entry-exit instrumentation using an instrumented library. This is developed as part of the STEP project. And with event-based sampling, I can see what each thread was doing, how many samples it received, how much time was spent. And with call path profiling, I can expand the full calling context. I can see where the application spent its time along which calling path. And atomic events can show you of maximum, minimum, mean value, standard deviation, number of samples, and the total volume of data. So if I'm seeing the bytes written, I can see on a file-by-file basis how much I/O took place on each file. As we scale up our applications to large number of MPI ranks, I/O becomes an important problem. And you may want to see how you are doing in terms of I/O operations and even the read and write bandwidth that you're getting on each file. And you can see all this along a calling context and see where your I/O takes place, how much I/O takes place to each file. And you can compare ranks. You can see the time spent in, say, node 5 or MPI rank 5 with rank 0. And you can see that MPI BCAS took 1 second in rank 0, but it took 29 seconds in rank 5. Here is an example of comparing not just within a rank, but entire executions, where I start with a code that's taking 528 seconds. We optimize it, it takes 528 hours. Then it takes 271 hours, and then finally it takes just 70 hours or 13%. And you can see where the time was distributed. Here, 134 hours were wasted in the MPI barrier. You can also view a particular event along its topology. So here I'm seeing 48 racks of a system, and I'm seeing the time spent in MPI all to all V. And each color is going from like 1.5 seconds to 2.6 seconds in the actual physical location of the nodes. Here is an example of running an application and measuring this time spent in FFTW function on 512 ranks. But these 512 ranks were not contiguously allocated. I had some ranks that were in this cluster, some here on the physical layout of the machine. And it's showing me where those ranks are on the physical machine. And I can look at the performance of this application, see the MPI all reduced timing across the full machine. Here I'm visualizing 786,000 MPI ranks. Along this direction, MPI ranks, I can see the function names and see this in the 3D visualizer to see the shape of the profile. Now, tau can be easily installed using the extreme scale scientific software stack, or E4S. E4S is a community effort to provide open source software packages for developing, deploying, and running scientific applications on HPC platforms. And it has built a comprehensive, coherent software stack that enables our application developers to be more productive. It uses a curated SPAC-based software distribution. We have over 120 HPC applications like OpenFOAM, GROMACS, NEC 5000 lamps. We have electronic design automation and even AI/ML packages such as NVIDIA NeMo, Hugging Face Hub, TensorFlow, PyTorch, TorchBraid, scikit-learn, Pandas. All of these packages optimized for GPUs. We have support for launching these in containers or on the cloud platforms as well. You can do a bare metal install. You can have containerized deployment with support for GPUs using even x86, Power, or AR64 ARM platforms with support for GPUs from NVIDIA, AMD, and Intel. And these are container images which can be launched. We have some additional tools like a tool to chain to SPAC instances so that you can install new packages in your own home directories while reusing the dependencies from a centrally installed directory. We have a tool to launch MPI applications in a container so that you can swap the MPI from within the container to the system MPI. And we have even tools to customize your container images and use SPAC to install new packages and create new images. We've had a recent release of 24.11, and it has over 132 different HPC packages and a large number of AI/ML packages as well. We have support for the MI300A or MI300X accelerator, new languages like Chapel, new applications, and upgrades to the vendor runtimes. We also have support for a multi-user, multi-node cloud-based image based on SPAC. And you can learn more about it at these URLs. SPAC is what is the underlying technology used by E4S. It's the package manager. And to use SPAC, all you need to do is just launch the SPAC command. But to manage the complexity of E4S, you can see that to build the 100-odd packages in E4S, which are shown in red, you have 600 other packages that need to be built. And it's not feasible to do this manually. So you can just clone SPAC, you can source it, you can find the compilers and external packages and just say SPAC install tau. It will build tau and install it, but you can specify a version with an @ symbol, such as install tau version 2.34 with GCC compiler. This is the percentage for a compiler, which is found in the compiler find command. And then you can specify variants. If you say SPAC info tau, it will show you these variants of MPI, Python, threads. And you can even say, for the MPI, please use mvaph2. And this provides the MPI as a package. Please visit spac.io to learn more about it. And I'd like to show you how this works on the cloud platform. And we have the E4S on the clouds using ParaTools Pro for E4S. And if you are wondering, if you want to transition your workload to the cloud, which cloud platform to choose, whether it's AWS or Oracle or Google or Azure, well, why not all of them and have a common environment? Our workloads typically need low latency, high bandwidth, and we need integration with GPUs, Slurm, Torque, schedulers. And if you try to build an image yourself with a base, say Ubuntu image, it's too steep a learning curve. And every cloud provider has interfaces that can be cumbersome to use. So we've looked at different cloud MPI options, and we have chosen MVAPIC because it has good performance on the inter-node network adapters, such as Elastic Fabric adapter on AWS or InfiniBand on Azure, or the Mellanox ConnectX-5 on OCI or IPUs. But it's more than just the inter-node that you have to look at. You even need high-speed intra-node communication. So you need XP-MEM installed and the MPI to use that, and support for GDR. And we are building this whole ecosystem of tools and using adaptive computing's ODDC to launch the E4S image on multiple cloud providers. Here is an image of ParaTools Pro for E4S, which is accepted in the AWS, Google, and Azure marketplaces. And you can see the listing. This is part of a DOE SBIR program. And you can search for the image, subscribe to it on Google Cloud Marketplace or Azure. And then you can use that image in the HIDE workshops or ODDC interface provided by adaptive computing, and then launch using the same interface on multiple cloud providers. So we have a session which we have added over here at paratools.adaptivecomputing.com, and we can do this. And yes, you can all have a hands-on session. For the hands-on, you start with tinyurl.com/E4S-tute, get the slides. I hope you are all able to go here and then click on this paratools.adaptivecomputing.com. I recommend using Firefox. And you will see a screen like this. You just click on the student, put in your name and email, and put this session code that I have launched. This will get us an AWS cluster. And you can all log in using this 33530 session code. When you click on this, after clicking on this student and click on the training session, you will see a cluster like this. And with this, you will be able to click on this and open the VNC viewer. And it will allow you to, allow pop-ups. Please allow pop-ups for this paratools.adaptivecomputing.com. And that's it. If you allow the pop-up, whether it's in Safari with a little icon like this or Firefox, you'll be able to launch a remote desktop. Without installing any software on your own laptop, you will be able to click on activities and get this remote desktop. Click here, click on the terminal, and launch a terminal. With this terminal, you have access to a home directory. Each user has their own home directory, and you are all able to go and access it. This is the starting URL, and then this is the URL for the paratools.adaptivecomputing.com. And then you can even right-click, go to preferences, change the font size, make it bigger by clicking here. And then you can run the commands like spac find -x. It will show you that we have 178 packages installed. There is a GPU on the login node. There's GPUs on the compute nodes. And then you can launch an application. You can go to, say, examples, CoMD, SRC MPI, type make, build it, go to the bin directory, look at the tau.qsub file, and just launch it by saying qsub tau.qsub, monitor your actual execution. And then you'll see profile files. You can launch paraprof and visualize it. Go to the thread statistics table, look at the time spent in the code, see the source code, and so on. So let me just try this with you. What I'll do is I will go to Firefox here and say, go to paratools.adaptivecomputing.com.
And Samir,
And
while you're doing that, there is a question in the chat. I can read it or you could look at it. Do you have any motivation or plans to support one API? Carl?
absolutely. We
Okay.
already support one API. DPC++ SYCL is fully supported in Tau. You can see the events occurring on Intel GPUs. You can see OpenMP, OpenCL. You can see OpenACC. We have support for LLVM compilers. We have support for level 0. So if you say tau exec -L0 a.out, you will see all the events occurring on Intel GPUs. Carl, I hope I answered your question. So go to paratools.adaptivecomputing.com, and then as you see over here, there is a code 33530. I'm going to put my name here, Samir Shende, samir@uoregon.edu, and the code is 33530. I'll say 33530, and I'll click on the training session. It will authenticate. I do not have to install any other software. I want to just access the cluster that's provisioned on AWS. I'll see this link here. I'll click here, and I'll click Open VNC Viewer. It will load it, and I'll get a remote desktop. It will connect to it like this. Okay, so let me just go here. And in this case, I will. So here is a desktop environment you can see over here. Let me just get rid of this terminal window, start it again. And I hope you'll all be able to do that. Just click on activities, click on these 9 dots, and click on this terminal. Can somebody confirm that you are able to go here and launch this, connect to the cloud systems, get a terminal window like this? So the first time, it expands the home directory, and it will take some time. If I want to see if it is fast, here is an examples folder. I'm going to the CoMD directory. There's a src mpi. Okay. So this is the first example using event-based sampling. All I'm doing is, like on slide 98, I'm going to examples CoMD src mpi. I'm doing a make and then going to the bin directory. Everything I'm doing is there in these slides. So here I say make clean, make, and it's building this example with -03 optimization turned on with -G. And it creates a bin directory CoMD MPI. So I can go to this bin directory. Here is a script here. There is a CoMD MPI binary. You'll see that MPI is already in your path. This is a simple MPI application. I have a comd.qsub, and I have a comd.tau.qsub. The only difference between these two files is that instead of running it with MPI exec with comd MPI, I'm adding the tau exec -EBS in front of this. Okay, so if I did a qsub, omd.qsub, I would be running the uninstrumented code. I'm running it on 2 nodes with 2 processes per node. And you can see if I say qstat, I'll be able to see that this is running now. And I'll see the output in this output file. Okay, so here is the output of the code. It's running through this loop, and there it's completed. Now to run this omd.qsub with a tau.qsub, I just added this tau exec-EBS. And I can say qsub tau.qsub. It will run the same application with no change to the source code or the build system or the binary. It will just simply launch it with event-based sampling with the tau exec tool and run it on 2 nodes and generate the profile data. To answer a question from Sagnik Singha, when you install tau, yes, paraprof gets automatically installed and it's in your path. You do need to have Java in your path, and you can install it without any root privileges. Even with SPAC, you can just say SPAC install tau. It will install it with no root privileges, just in your home directory. Tau does not require root privileges. So here, I see that this second job has also completed. The status is C, and I see profile files. I can simply launch paraprof like this, just like my slides show over here, that you say qsub tau.qsub, and then you launch paraprof on slide number 100. And then you can right-click here and see the node, see the thread statistics table. Like on this rank, node 0, thread 0, I can right-click over here, and then I'll be able to launch the thread statistics table by going to this show thread statistics table and clicking on it. So is this okay? Are you able to open up like this? So here, I see the inclusive time, the total time in the application is 26.7 seconds. This is MPI rank 0, thread 0. The time spent wasted in MPI collective operations in a MPI barrier is very little. It spends, say, 0.1 seconds in MPI in it, 0.03 seconds over here. I can click on this and sort it, click on it again. And what this is showing me here, let me just expand this window, is that the application took 26.7 seconds. The preload main function spent 26.3 seconds outside of MPI calls. Out of the 26.7, 26.3. But with sampling, I collected 859 samples. You see the context over here. Sampling is like throwing darts on a wall. It is imprecise. What this is showing me is that I can explain 25.7 seconds out of the 26.3 seconds. It's not the same, it's a little less because of samples. So let's see what these 25.7 seconds look like. Here are all the MPI calls, and then inside the application, I see that out of the 25.7 seconds, 24.3 were spent in just one function called LJ force. Now here, There are other functions too, advanced velocity, sort atoms in cell, get box, but it's saying those got a very few samples. The most of the samples came from LJ force. And so if I click on this, I can see that out of the 24.3 seconds or 812 samples, 154 of those came from this line 198. It took 4.6 seconds at this line, which is line 198. If I right click here, I should be able to just see the source code by saying show source code. And that's the line. That's the line in the code where it's spending 4.6 seconds. You can see that this is the function LJ force. And how much time was spent here? 24.3 seconds in LJ force, and 4.6 seconds came from this particular line. So it drills right down to the code where it's spending time. And this line is actually in a for loop. Well, more than one for loop. There's 1, 2, 3, 4, 5 levels of nesting in the 5 for loops. And this line of code in this molecular dynamics application, it was calculating the LJ force between the atoms. So here we see the time spent in that particular line of code, and line by line, we can see the breakdown. This is line 199, which is spending 3.36 seconds, and that's the next line. So you see, this is an important loop in the code where it's spending its time. So I'll take a chance to redo what I just did so that everyone is on sync. First, I went to paratools.adaptivecomputing.com. I got a session started over here. Like this. I went to paratools.adaptivecomputing.com, clicked on the student tab, put in my name, email address, and this code. Is everyone okay with this? Then
finally, Samir, I finally was able to log on to the cluster because I'd forgotten how to use the PIM key and I missed your instruction on that. So I'm finally on a cluster. I don't know about anybody else. I got through that part fine, and I got to the control panel, and then on that.
You allowed the pop-up, got the VNC viewer.
Yes,
and then you got this window, right?
At one point I did, but what I did was I just opened up a terminal window and started.
Yes. So you clicked here, and then you clicked on the terminal window, and then you, after a minute or two, you got a screen that looked like this, right? Your own home directory, and you had a terminal prompt.
Yes, sort of. I didn't even try that screen. I wasn't following your instructions, but I was able to use the PIM file and do it from the command line terminal app on my laptop.
Oh, using the PIM file. Okay.
Yeah, so because I couldn't make the other window work, but again, I was having trouble always.
Were you using Firefox?
Huh?
Were you using Firefox on Mac?
I was using Chrome.
Okay, so I'd recommend Firefox.
Okay.
But in any case, you just need to enable the pop-up window. That's the key part.
Okay, so that's just for anybody else who sometimes I get busy and I don't always follow all the live instructions. So I am now on a system just to be caught up.
Okay, so you can then go to CD to the examples, CoMD, SRC, MPI, type make, go to the bin directory, type qsub, tau.qsub, and then you will be able to say pprof or paraprof. It's the GUI tool will work better with the integrated desktop.
Okay.
And then you'll be able to launch this. Is there anybody else who has been able to go through these instructions and start over here? Go to paratools.adaptivecomputing.com and click on student, put in your code here, click here, open VNC viewer, use Firefox, allow pop-ups for ParaTools. You will get, or with Safari, and then get to this screen. It is working now for you? Okay, great. No problem, Masha. Sagnik, yes. Tal, okay. And you are able to get the terminal window? Are you able to go to terminal here? CD to the directory? Like this, examples, comd, src, mpi, make it CD to the bin, qsub, tau.qsub, launch paraprof, open up the right click here, open up the thread statistics table, click on these inclusive, exclusive times, expand, 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 go to the LJ force, click show source code, and see this line of code that the application spent 4.8 seconds in. So this is working. You are able to launch paraprof and see the data. And we just a few people. It's okay if you just unmute yourself and speak. I'll wait for everyone to catch up. I hope you are able to see this. Any questions while we wait for others?
Can you give that path again to the, I went through the desktop app and that's working. And
that's working, great. CD
yeah,
examples, comd, src, mpi.
Examples, comd, source MPI, okay.
Yeah.
I am in the directory.
And then are you able to type make? You can say make clean, make. It will build the application. It will put the binary in the bin directory.
Okay. And then
/bin.
Okay, that's working for me. Okay.
And then you're in bin directory. You can launch an uninstrumented binary with comd.qsub or a tau with qsub tau.qsub. And you see the only difference here is this tau exec-ebs that's added before the name of the binary.
Yeah.
And then you say qsub tau.qsub, you're launching it on 2 nodes with 2 processes per node. You can say qstat and check the job status. It will show either queued with a queue, R with a run, or S with a, or C with a complete.
I see. Okay, I see I had to change directories to find the tau.qsub file. So I saw that.
CD /bin, like here. And then qsub, tau.qsub.
All right, I've submitted it and I have a job in the queue. So
excellent.
now I just have to wait for that all to fire up. Will it launch a terminal? It will launch
and then once the job completes, you will see profile files in your directory, and you should be able to say paraprof like this. And then you should be able to look at the thread statistics table by right-clicking on it.
I launched the tau qsub from the ComD
login node.
directory. I don't see
No,
any
no,
yet.
it should be in the bin directory. You should be in the bin directory where you say qsub tau.qsub.
Okay, I see the data. And now what do I type next?
Paraprof
Sorry.
ampersand.
Okay, paraprof, got it.
Do you see two windows appear like this?
I do see two windows. This is great.
Then right click on node 0, thread 0, and pick the third option, which is show thread statistics table. Right click.
Yep.
And then you can click on the inclusive time column. It will sort it. Click it again. It will sort it again. Then expand this tau preload main. Expand it. You will see LJ force is red hot. And expand the LJ force. You'll see line 198 at the top. And
Okay.
then right click over here at line 198 and say show source code.
Show source code. Okay, I see the
And
source.
do you see the source code, the line of code where it's taking 4.8 seconds? And this is in 5 levels of for loop.
Line 197.
Oh, well, it's, I think 198. It's
Yeah.
just.
Yeah, it's a little offset. Okay, the DR of M.
Yes, exactly. Does that show up properly?
Yes, it does. My screen looks like yours.
Perfect. So you can
Thank you.
see line by line profile for each rank of an application with no change to the binary. You just said tau exec-EBS and launched paraprof right after running the code.
This is great. And you can see the exact line that's
Exact line of code.
consuming most of the time. Okay. I hope this helps everybody attending to see me navigate through this, and maybe you've been able to catch up and run the tau example. Thank you for your patience.
Are others also able to see paraprof and see the performance on a line-by-line basis? Yes, Masha, good.
Yuzhong is working, Masha is working, so this is great. They're all Yuzhong, yeah, it looks like several people have it working.
Now
So,
we should go to an example that uses PETC. This is example 2. And here I go to examples PETC CPU. I'll say compile.sh and then run qsub tau.qsub, check with qstat, and after it completes, launch paraprof. The same thing that I have done before with tau exec-EBS in the PETC CPU. Okay, and then once you see the qstat, you can again launch paraprof and view the performance data and see the application and where it's spending time, or pprof. And then I will generate trace files using this trace.qsub, which I have put in the temp directory. You have already compiled the code, run it with trace.qsub, and launch perfecto.dev in Firefox, and open the trace visualizer and view the trace file. To do this, again, I am in slide number 104. Step by step, I'll do exactly these steps. And I'll go to examples, PETC, CPU. Say if I had a clean.sh, I say compile.sh. This is using E4S. It's just doing the makefile. It's loading PETC without CUDA. I'm saying compile.sh first here with CPU. And there it is. All these libraries that you see over here come from E4S. If I did an LDD on the executable, or executable which is called EX50, you will see that all of these libraries are installed using SPAC and E4S, like libmatis, MPI, Super LU, Hyper. I have this EX50 application, and here is the ex50.qsub file, how I run it, and here is the tau.qsub. And you'll see the only difference here is I added a call path, and I'm running it with tau exec, like this. And I also have a tmp trace.qsub, where I added the tau trace equals 1. I merged the traces. I converted into an app.json that can be then viewed in this way. So here are profile files that my program generated. It's completed. The status is C. I can launch paraprof and view the profile files. Here is again, right click here. I can see over here in paraprof many windows. I'll choose the thread statistics table. And I can see over here tau application. I open it. I can see MPI bcast. And see, this is the time wasted in the code in a barrier call within the bcast when it was called from here. I can right click here, even say show function bar chart. See that this is so much time wasted in barrier in MPI collective sync. But let me just go down to the application. I click on inclusive time here. And these are the calls from PETC. You see all these functions, mat LU factor is taking 0.133 seconds. And I can see exactly what's happening at which point in time and what it was doing in this mat LU factor with sampling, and there's a libmatus, there's a GK short one, and sometimes you'll see a line number as 0 because that library has not been compiled with symbols -G, but still you can see the name of the function and you can see exactly which calling path it came from. This is a call path profile. So the steps are pretty much the same. I just used PETC CPU, did a compile.sh, qsub, tau.qsub, ran it, launched paraprof after it completed, and then I could view the data with the thread statistics table like this. Is this okay? Are you able to launch paraprof with this? Because next we will copy this trace.qsub and then run this and launch the trace visualizer. So Mary, does this work for you with the qsub?
I'm working on I didn't have a chance to try it yet. Sorry about that.
Okay, so
the
just
Hopefully somebody
visualizer,
pardon?
right from the cloud or from the local host?
This is all running on the cloud. Everything is on AWS. There
Okay.
are 2 compute nodes with a GPU each, and then there's a login node where we are running the paraprof browser. It's getting rendered on the cloud too.
I mean to the Google Trace Visualizer. You should run it from the cloud as well, right?
Yeah. Everything is on the cloud. The perfecto.dev as well.
Okay.
You can launch Firefox from within Firefox. That's what we are doing here because it's reading the app.json file. So all you do is do the compile.sh, qsub it, run it, launch paraprof. Then say qstat, see that it completes, launch paraprof, Again, right click on a particular rank, see the thread statistics table, and expand the call path. You can also use pprof to see the text output for the profile data. And this is the next interesting part where you can see the traces. So while we are waiting, I'll just mention that we have a 3D visualizer here. It can do bar plots, a whole lot of interesting visualization. You can click and rotate. You can zoom in, zoom out. You can use the second mouse button to translate. This is Windows 3D visualization. And here, if I copy the temp trace.qsub over here, I can just say qsub trace.qsub. Here is the trace.qsub file. All I'm doing is setting tau trace to 1, then merging it, and then converting it to app.json. And when it completes, I'll have the app.json. You can see that this is completed. I can just say Firefox https perfecto.dev like this. And then I go here to trace viewer. I say open the user interface. I can say open the trace file, and then go to my training examples, PETC CPU, app.json, and click open, and it will load the trace file. Here are the 4 application threads. And you can see what each of these threads was doing is an MPI init thread, is an MPI init thread, MPI init thread, and then this is where the application starts. I can see the mat LU factor over here. I can click W to widen. I can click S to shrink. I can go over here, click release. In this area, I can go to WWW and widen this and see that this is main stage calling KSP solve, calling PC apply, mat solve along a timeline. I can see what each of these 3 MPI ranks was doing and see the MPI barrier over here. Okay. I can do a D. Print it. Now I have the same application available, the same PETC running with CUDA as well in the PETC CUDA directory. And it's the same workflow, compile.sh, and maybe copy a different trace file here. With CUDA, and I'm running this with kubectl. I can launch tracecuda.qsub, temp tracecuda.qsub, launch it, and launch perfecto.dev like this. Let me just remove any. I'm going to copy tmp trace CUDA.qsub here in the PETC CUDA directory and say qsub trace CUDA.qsub. So it's just compile.sh and then run this bench KSP solve, which is now using CUDA. And you can see here, it's running on 2 nodes. I'm saying spac load tau with MPI and CUDA, and say tau exec with the configuration of kubectl, enable the kubectl, and run the application. So just enable tracing, run tau exec like this, merge and convert the traces, and then launch it using perfecto.dev. And here are the trace files. I have app.json. Looks like it's finished. And I can say Firefox perfecto.dev and launch it. Again, I click trace viewer, open the user interface. This is made by Google, the visualizer. I'll click the open trace file. I'll go to the examples, PETC CUDA, go to app.json. It's loading the trace file. And I can open it. I can see what's happening on the GPU thread, on the CPU thread. I can expand these 2 MPI ranks. This is CPU, this is GPU. I can say click and release and just widen, W for widen, S for shrink, A to go left, D to go right. Can you see the name of this kernel? It says kusparse. Kusparse tsrmv. This kernel running on this GPU thread. You can see there's a CUDA memcopy, async, vector scatter begin, all of these operations in CUDA operations, and you can see what each rank was doing at any point in time. Here I'm moving. And events that happen with CUDA. Here is one kernel, here is another kernel, kusparse, 2 kernels running on the GPU. Here is a memory copy event, host to device, device to host. So you can see exactly what the application was doing at any point and see details of data transfers. You can see memory copies, what happens when in each MPI rank with no change to the binary, no change to the source code, no change to anything, just you launched it with tau exec and you can see the execution on the GPU. And all I had to do this was I go to this directory, PETC CUDA, and then I simply copy this trace CUDA.qsub over here, qsub it. First, I have to do the compile.sh. And then I run the qsub, launch Firefox, and open the user interface. We are coming up against the end of the hour, but I can keep the system going if you are interested in running these applications. But I hope this was a quick introduction to tau and see how easily we can change the batch submission script and go from this to tau.qsub, this, and simply launch it.
Samir, we have a couple last questions in the chat. How to interpret these graphs. And for instance, in the first node, I see tau app runs the longest and short runs. in other ones?
So the .tau application is just a top-level dummy timer. It starts from the very beginning of the application and ends at the very end. So it tells you the total inclusive time in the application. That's all. And when there is a child function that is instrumented, like an MPI in it, it takes away from this .tau application timer. So its exclusive time is what is left. Do we have access to the training site after the training? So AWS charges me by the hour. I can keep it running for, say, another hour while you continue to use this and see the slides. Is that okay? And you can try several examples here. And I hope you found this useful and were able to log in properly and try some hands-on. Here is the widen, shrink, left, right. There's a 3D visualizer. And there's some reference material in the slides as well. I'll take this moment to thank the US Department of Energy, NASA, Department of Defense, NSF, CEA, our industry partners and partners at other educational institutions, and the US Department of Energy Office of Science, the STEP program, the PESO project that are funding this, the DOE SBIR project that has helped us create this web-based training offering. And E4S is part of the High Performance Software Foundation, HPSF. You can learn more about it at these sites. And this E4S project was created by the Exascale Computing Project. So I hope this was useful, and you can apply Tau to your workflows, and please get in touch with me if you would like me to help you install Tau, or just reach out to me. Here's my email address, and I'll just keep it running. It's 12:30 p.m. Pacific time, and so.
Yes, another quick question, Samir.
Yes, please go ahead. Can Tau
thank you
combine the instrumentation mode with sampling mode in one
Yeah,
application?
that was my question. Like in the same run of Tau, some
Yes.
of my
Absolutely. In fact, that's what we did here. The MPI instrumentation was in instrumentation. You can also have source instrumentation or any other instrumentation. Here is CUDA with sampling. So we just say -kupti -EBS. Whenever you say -EBS, it enables event-based sampling. So you can have them both at the same time, which is what we did when we did this. The MPI functions were instrumented using the wrapper library, and then event-based sampling was to show you the source level data.
Thank you very much. It was very useful.
So please try this PETC CPU. All you have to do is say compile and run qsub. The same thing with the GPU code, and you are able to see the profiles with CUDA information, and all of you can use 2 different nodes and launch it. Just say temp trace CUDA.qsub, compile it, run it in the examples.
Thank you. May I have a question still regarding event-based? I'm a little confused, event-based versus what you said about every second or every millisecond. So how does the event connect to those timing intervals?
So what event-based sampling allows you to do is, with source probe-based instrumentation, you have the entry and exit. And with sampling, you just get a stream of interrupts every 30 milliseconds. So based on the number of interrupts that you receive at a particular point, the program counter, and then based on the sampling interval between these 2 interrupts, Tau estimates that the total time spent in line 198 in this LJ force is 4.8 seconds, because it collected, say, 159 samples there. Okay. Whereas with MPI, you have the exact entry and exit.
Yes, of course. But what is event? Maybe what is event, definition of event? I missed that.
So event could be an interrupt from the operating
Okay.
system.
Got it.
It could
Thank you.
be a periodic interrupt. It could be even a hardware performance counter overflow. So you could say, instead of wall clock time, I want to be interrupted every 100,000 data cache misses. And then after 100,000 data cache misses elapse, they'll interrupt your code.
Okay, yeah, thank you. That's a very helpful clarification. Thank you.
Great.